Okay, so I have the pleasure to introduce Dr. Beren Millidge from the MRC Brain Networks Dynamic Unit at the University of Oxford. Beren received his doctorate in machine learning and computational neuroscience from the University in Edinburgh in 2021 and joined the group of Rafal Bogage at Oxford as a postdoctoral researcher that same year. Beren's work focuses on the intersection of machine learning and computational neuroscience. And in particular, he's done a lot of work on several aspects of the free energy principle and its process theories. For example, he has critically assessed the standard form of the expected free energy functional, and he has demonstrated how predictive coding approximates backpropagation on a large class of commonly used machine learning models, thereby showing that something close to backprop might actually be more biologically plausible than generally thought. And one thing that I want to stress in particular is that Beren is one of a number of younger researchers who are putting a lot of effort into writing really good reviews and tutorials and making the free energy principle much more accessible than it notoriously used to be, which is a merit that can hardly be overestimated. So, Beren, we are glad to have you here, and I'm excited to see what you're going to present today.
So I'm not here today to talk so much about my work on the free energy principle, although in the discussion time, I'm very happy to answer various questions about this. I'm mostly basically towards trying to talk to you about my work related to predictive coding and understanding how credit assignment works in the brain and how it relates to different algorithms like backpropagation of error. And so this is I started this work in 2020 during my PhD at Sussex and have continued on with it for the last 2 years. And so this is really my most up-to-date findings and thoughts about this. And so probably the paper that most of you, well, if you know about it, you will know is the predictive coding approximates backprop paper. And so we'll go through that and also think about further, how can we develop this and what can predictive coding say more about how learning and inference actually works in the brain. So the way to start out is to think about, first off, what is credit assignment? And why is it necessary? So credit assignment is fundamentally the problem of your brain obviously has many, many, many neurons, and most of these neurons are quite far away from any kind of supervisory signal. So if you suppose you have visual neurons, most of the neurons in your visual cortex aren't in direct contact with your retina, but yet still they need to figure out basically when to fire, how to fire, what to do to actually produce useful visual representations. And so somehow information about what to do at your retina, say, or at the site of action must be somehow transmitted backwards through your brain, so you can actually basically neurons deep inside your brain, which only connect to other neurons and don't have any direct supervisory signals, will know what to do. And this problem is fundamental for any large neural networks. And so this is fundamental in machine learning. And really it's the solution of this problem in machine learning by backprop, the backpropagation of error algorithm, which is what essentially created all of modern machine learning and the fact that it actually works. So this problem is fundamental, and we still really have no real idea how the brain actually does perform credit assignment, whether it performs backprop like our current machine learning networks, like our artificial neural networks, or whether it does something different. And I used to think it did backprop or approximated backprop, and now I think it does something different. So there's been some evolution during my research time. But anyhow, so that's the fundamental problem I'm trying to tackle. And I think this is one of the most important questions in neuroscience. It's really a fundamental thing about how the brain operates. But it's also something that not many people study. So that's actually quite a nice niche. And as well as trying to understand the brain, this is also having answers to how the brain could do this is actually very important as well for machine learning. And so there's several reasons for this. So the most obvious is really that the brain is currently the only known system that actually exhibits fully general intelligence like us. And so if we understand how the brain works and understand the fundamental principles of learning in the brain, we could then implement that obviously in machines and potentially do better than what current machine learning is doing. Well, it depends. If you think current machine learning is sufficient for general intelligence, then it's not so important. But if it's not, then it's obviously quite important. And so similarly, we think a lot of the basically the properties and algorithms we find in the brain can actually transfer over to machine learning because the architectures are actually incredibly similar. And so there has been this amazing convergence in machine learning basically towards artificial neural networks, deep learning, all this stuff is incredibly similar to the actual architecture of the brain, at least compared to how artificial intelligence was before machine learning to deep learning took off. There was all these decision trees and tree search and logical rules and stuff, and various like SVMs. None of this is actually related to what the brain does, but the one thing that actually did work at scale is very brain-like, and I think that's very important. And so it also means that we probably should expect a lot more transfer between like the computer science, machine learning, and neuroscience than we would sort of naively expect. And so final reason is that personally, I think, and this is a controversial viewpoint in neuroscience, that the brain is actually highly optimal. And so it's very close to being optimal given its constraints. And most of these constraints relate to efficiency, but also efficiency in terms of energy, efficiency in terms of space, but also efficiency in terms of like learning speed and data. And that the brain obviously has to operate with relatively little data compared to sort of state-of-the-art machine learning methods where you can like scan the entire internet and like download it and let your neural network see everything. That's not possible for the brain. It has to be able to do like adaptive behavior very quickly. And so the learning principles that underlie the brain's capability to do this could actually be very useful for current machine learning methods as well. So like, I'm going to give you a quick overview on how backprop works. So backprop is the fundamental algorithm that does credit assignment in deep neural networks. Probably like most people know this, I'm going to be go quite quick through here. But if anyone has any questions like about this or anything in the talk, please just like stop me and ask. So essentially in backprop, we imagine like we have a neural network. So imagine these X's are like layers in a neural network. And so this is just like a simple sort of chain style architecture. And so we define each sort of the activity of each layer, like X1 is just some function of the activity in layer 0. And this goes through all the layers until we reach the output. At the output, we compute this loss function, which basically says like how good is the output of the network compared to what we want it to be. And then given this, we can basically compute gradients backwards. And so the idea is we want to compute a gradient, say, of the weights like here, given this output. And what backpropagation does, using the chain rule of calculus, it tells you that to get the weight update here, you could start here and go back 1, and then compute this gradient, and then multiply that by this gradient, multiply that by this gradient, and then get your weights. And so backprop is this sequential process of just computing the gradients essentially in the reverse order that the original computation happened. And so like the first most obvious thing, right, is if backprop works so well in machine learning, and like basically we know it works extremely well, then why doesn't the brain just actually use backprop? And so obviously you could say like maybe there are better things to backprop, the brain does that, that's very possible. But also there's like serious problems with like a naive implementation of backprop given the circuitry we know about the brain. And so several of these problems are, one is that the sort of fundamental thing in backprop is that there's this forward pass, and then there is this backwards pass, and the forward pass happens, and then the backwards pass happens sequentially. And so this is not something that happens in the brain. In the brain, you have essentially constant like inference sort of iterations, recurrent sort of connective, like transmissions going on all over. There's no like forward pass for your brain and a backwards pass for your brain. And so similarly, we have this other issue with sort of sequential transmission of information. So, in backprop, to compute the gradient here, we first need to compute the gradient here, and then compute the gradient of the loss. And so basically, while, the gradients are not actually computed, so, basically x2 here is like waiting for a bunch of time while all these backwards gradients are computed. And so this has to be done sequentially. Whereas this doesn't happen in the brain. In the brain, everything appears to be pretty parallel in that we can just like run sort of the brain, I guess, and then everything is kind of, all the neurons are firing. There's no like sequential sort of phase locked neurons, like first V1 fires, then V2 fires, then V3 fires, and then on the backwards V3 fires, then V2 fires, and V1 fires. Like that's not what happens at all. And so those are the sort of two main issues relating to parallelism. And then there are other minor issues with the algorithm itself. So like one issue is basically that the weight update is kind of non-local. If you assume there's like a backward set of circuitry to compute all of these neurons, then the weight updates here are used in the forward pass, but then they have to somehow know about the gradients in the backwards pass. So this sort of transmission from here to here is non-local. And secondly, is that if we suppose we're going backwards, we need to know what the forward weights are, but then the issue is obviously that in the brain, sort of axons, like synapses, all of this stuff is unidirectional. So we can't go back through the same circuitry we came. So there needs to be like this separate set of circuitry going backwards. And then how do we keep the forward circuitry and the backward circuitry in sync is essentially the problem. And this is called the weight transport problem. So there are various issues with backprop. And so a relatively small, but like I think quite cool literature has grown up about like how do we deal with this? How can we make sort of biologically plausible backprop or algorithms that approximate backprop? And so there's a whole bunch of them. And so what really kicked off this field was this Lillicrap paper from 2016 called Random Feedback Alignment. And the only thing this does is deal with the backwards weight problem by basically saying that instead of computing the backwards weights with like the same as the forwards weights, you just take the backwards weights here to be some totally random matrix, and then mysteriously that actually works quite well, at least for like relatively small tasks. So similarly, there's this other various set of algorithms called equilibrium propagation, which comes out sort of this group by Yoshua Bengio, and this is all about like running the network in multiple phases and then updating the weights of the difference between these phases. And so that's one set of paradigm. Another paradigm is predictive coding, which is what I've been mostly working on and will be telling you about today. And so this sort of started out with this paper by James Whittington in 2017, where he showed that in some conditions, predictive coding can approximate backprop on these sort of chain-like graphs. Then obviously I did some work on this in 2020 and showed that you can extend this to arbitrary graphs under different conditions. And so this means basically any machine learning architecture you want, you could basically do backprop on it with predictive coding under certain assumptions. And then my now collaborator, we weren't collaborators. We weren't really competitors either, but anyway, Yuhang Song showed like under a different set of conditions, a very similar result also at the same time in 2020. And so I'm going to talk about predictive coding networks, but basically the fundamental idea is in predictive coding, you essentially have like errors spread throughout the network, and then these errors are sort of iteratively minimized, basically locally minimize their own error. And in doing this, you can show the sort of distribution of error that emerges at the end can be made to sort of look very similar to the gradients in backprop. And then because of this, obviously, if you have those gradients, you can approximate backprop. And so another thing, which is very interesting, is that recently, I'm not going to talk about this paper, but recently I also have a paper out showing basically how all of these equilibrium propagation, contrastive Hebbian learning, and predictive coding can all be kind of seen as the exact same thing. And there's like a unified framework which can explain why all of these approximations to backprop occur. And so that's really fun, and I have a paper on that, but I won't be talking about that. I'll be talking about my other fun paper this year, which is about essentially what happens when we don't try and approximate backprop. And so that's lots of interesting things there. But for now, we're going to continue with how the backprop approximation works. So as well as approximating backprop, there are other things you can do. So essentially, there are multiple ways to optimize things. Basically, all you're trying to do is minimize some loss function given in your network. And backpropagation is one way to do it. Another way is this other algorithm called target propagation, which has a really nice intuition, actually. So the idea is that instead of backpropagating gradients, so instead of saying like for each weight, how should you change to minimize like the loss function, you instead propagate this thing called a target, which is like for each weight, what would be the sort of optimal activity at the next layer, the sort of local activity for you to produce. And then if you know that optimal local activity, then you only have to update the weight basically to minimize the distance between like the current activity and then the optimal target activity. And so the key difficulty in target propagation is obviously computing these local targets. The way they're done is like, the way to think about a local target is the activity at a layer that if the rest of the network was the same, and if the activity of the layer was somehow set to this value, then that activity would propagate through the network such that the output of the network would actually end up being like the correct classification or would minimize the loss. And so this sort of forward propagation of the target gives you sort of the intuition behind it. But in practice, what you can do is you can actually compute this by essentially inverting the network. So if you have, say, a target at the end, you want the target, and like the layers, then basically you take the inverse of that target back through the layer, and then that will be the target of the next layer, and then the target of the next layer. And so this is essentially this equation here, where the targets of the given layer are basically the inverse of the forward mapping from the layer above, essentially. And then basically you can derive these local errors between the activities and the targets, and then you can update the gradient using only these local errors. And this is obviously a highly local update rule, but it has issues with sequentiality, essentially, because you have to, like in backprop, you essentially have to sequentially go back through the network computing the local targets one layer at a time. And this is because obviously the local targets at layer L depend on the local targets at layer L+1. So it still has the sequential problem, but if you have these targets, then the weight update is local. So hang on, never mind. So anyhow, let me just check. I thought I had a slide about this. Yeah, okay, so I'm going to skip quite a way ahead, but this is essentially just a way to think about how the various algorithms work I've described. So in backprop in the middle here, we basically have a network going up. So this is like the forward passive model. And then we basically set gradients sequentially backwards. And so this is how backprop works. Target prop, which I just described, has activities to the forward pass going forward through the model, and then sort of these local targets, these inverses, being sent backwards. And so both of these have this fundamentally sequential structure, although target prop has slightly nicer locality properties than backprop. And then predictor coding, on the other hand, it has activities being sent up, and it has basically errors being sent down. But the key thing is that these errors essentially are minimized locally all the time. And so there are always local errors that are being minimized. And so you can run all of these minimizations in parallel, unlike in backprop and target prop, where you need this sequential backwards pass, essentially. And so obviously it takes some iterations of this, like some iterations of this like running to equilibrium convergence process is required to take the errors back from the output all the way to propagate them through the network, but it's not necessarily a sequential process is the key thing. So all these elements can run in parallel. Right, so now move that forward. Let's talk in a bit more detail about how predictive coding works and sort of the intuitions behind it. And so I'm gonna, if you guys kind of know about sort of inference in the FEP and stuff, you probably know a lot of this, but like basically the fundamental idea is essentially that your brain has to do inference, like it has to infer the causes of sensory stimuli, very similar to the FEP. And then obviously the brain, by doing this inference, you have to have powerful generative models of the environment. And so the question is, of course, how do you obtain powerful internal generative models? And so predictive coding says basically you can do everything by sort of unsupervised local prediction error minimization. So at the start, we have, we're trying to predict our sensory data, and solely by trying and failing to predict our sensory data, can we build a very powerful generative model of the world. So that's like the sort of abstract idea. And then you can specialize this to like specific architectures by saying like, if there's a hierarchy, of levels or layers somewhere in the brain, then each will minimize its own prediction errors and sort of make predictions of the layer below. So essentially this scheme can be generalized to a hierarchical structure, which is necessary to actually represent, like detailed causes and like latent states and stuff. And then it's sort of as in terms of like the implementation, what this results is the predictions end up being sent downwards. So essentially from high level layers to low level layers, where the lowest level layer is just like the sensory input, and then prediction errors are fed back upwards. So essentially each layer can figure out, what are the errors in its predictions going downwards, and then update based on that. And so there's a lot of evidence in about, well, I always like to use these hallucinations sort of, these visual issues basically, but there's a lot of evidence that your brain actually works in this sort of predictive way, that it actually contains predictive models of the environment and makes assumptions based on these predictive models. And so this seems very obvious kind of now, I guess, but like back in the day, people thought, the brain was just doing this feed forward sensory processing and doesn't sort of just parses the visual scene into features. And then this sort of feature view can't explain why we have various visual illusions. So like a classic example of this is sort of this kinesia triangle example. So even though you can basically see these white triangles on top, even though like there's actually no like lines here, you sort of see these weird illusory lines. And this is basically because your brain, the model in your brain, in the visual system, has a very strong prior about like lines being continuous and shapes and all this sort of stuff. And so this is basically making like top-down predictions, like there should be a line here. And obviously there isn't a line here, and that's generating prediction errors. But basically this showing you're not just parsing bottom-up input, but in fact you're essentially matching your input with a top-down prediction. And so a similar thing about the idea of prediction, although you guys kind of seen this because I've zoomed ahead, is that if you don't know what's here, this just looks like a bunch of sort of random dots and sort of strangeness, then you can't really parse this scene. But if I show you that there is a dog here, and then I quickly go back here, and then you can interpret this exact same visual data in a much more effective way, and you can directly parse that this is a dog, because essentially the latent variables in your visual cortex are updated, and it's like, I now know there is a dog here, and then this prediction comes down here, and then that gives you a phenomenologically different representation or visual perception of the scene. So there's lots of evidence in this way for this kind of model-based predictive processing. And so this is like, that's basically the standard justifications for this. And then nowadays in machine learning, there's huge amounts of evidence that this is fundamentally a thing that works as well. Like if you look at any of the large-scale machine learning stuff, like GPT-3 and stuff, this is all based on unsupervised prediction of sensory input. In GPT-3's case, this is text. And so this seems to be a very general principle about like how to form highly effective generative models. Right, so now that's an abstract high-level idea of predictive coding. And so now the idea is to try and specialize this and to design an actual neural architecture. And so for this, we try and stay as close as possible to like really basic machine learning, like multi-layer perceptrons. And so we can think about this predictive coding network as essentially being like this hierarchy of layers, like a standard artificial neural network. And the key difference is that instead of just having like the activation, activity, whatever, at a layer, we instead have both activities and we have prediction errors. And so the fundamental idea is we want to minimize these prediction errors throughout the whole network. And so the way we do this is we first minimize prediction errors, and then we minimize weights and relative to the prediction errors. But like the connection to the free energy basically comes from the fact that this sum of prediction errors, you can interpret this mathematically as a variational free energy term, and hence interpret what the whole network is doing as variational inference. And so really this predictive coding emerges naturally from the FEP if you make certain assumptions about the generative model. Specifically, you assume that it's Gaussian and hierarchical and all these kind of assumptions, then you can exactly derive predictive coding networks from the sort of high-level abstract FEP. So we can kind of make this a bit more specific. So predictive coding essentially assumes that you have this hierarchical Gaussian generative model. So what this means is we have these latent variables, x0 to xn, which all represent a layer in the network. And then we can basically split this up into a hierarchy of layers. So each layer only depends on the layer below, and where each sort of conditional distribution here is Gaussian, where with the mean of the actual activity, so the prediction projected upwards from the layer, and a variance of basically some variance, which doesn't really matter that much. And so then if we do some mathematical tricks and we assume a certain posterior, variational posterior, we can basically show that the free energy, as is the fundamental object in the FEP and the fundamental object in variational inference, can be written as the sum of squared prediction errors, and where the prediction errors is defined between the activity at a layer and the sort of prediction upwards from the layer below. So the way to sort of visualize this is to think about basically that there are multiple layers here. So this is layer L+1, layer L, and layer L-1. And in a sort of normal machine learning MLP, these layers would just, there wouldn't be any prediction error at epsilon terms here. There's just these mu terms, and then this would be going up directly. But here we basically introduce prediction errors at every single layer, which represent essentially the difference between what this layer is representing and like what higher up layers think it should be representing. This is the prediction error, and then each layer basically optimizes its activities to minimize these prediction errors. And so personally, I think it's very helpful to write things as an algorithm. So this is the sort of predictive coding algorithm very, very sort of specifically, is what we do is we have this multi-layer network. To do it, just make a prediction. We fix the input nodes. So basically we clamp the bottom of the network to whatever data you have. And then you do run this, basically update the activity node to convergence by minimizing prediction errors all throughout the network. And then we just output whatever the prediction is at the output nodes. And conversely, in learning, the only thing we do different in learning is we basically fix both the input to the data and also the output to the desired data, aka the desired target. And so then if we have this, we can update the activity nodes to convergence and then update the weights given the errors at the equilibrium. And so obviously, basically, in the prediction case, the only error coming into the network is at the bottom. And then during this convergence case, this error propagates all the way up the network slowly. But the key thing is that the error here can be reduced to 0, because basically there's only one constraint on the network, and so it can always satisfy one constraint. But with learning, there are now 2 constraints. There's error at the input, error at the output. Both of these errors during convergence, they propagate throughout the whole network, and then essentially they have to somehow balance each other. And so the network will settle into an equilibrium where like changing the activity in one layer will change, obviously, basically what it represents to the prediction of the data, but it also changes the prediction of the target. And so both of these errors essentially match at equilibrium. Then at equilibrium, we can update the weights in such a way to minimize just basically the sum of the prediction errors at the equilibrium value. So again, this is what the difference between predictive coding, backprop, and target prop. And so now we come to the first key result, which is how predictive coding can approximate backprop in general, so on arbitrary sort of computation graphs. And so the fundamental idea here is that first off, we need to think about what does it mean to do predictive coding on an arbitrary computation graph. And so essentially in neural networks, we can think about like each node here as being a specific operation. So in the case of multi-layer perceptrons, each node is just like a layer, and then this operation is just like the forward pass through that layer. But like we can define arbitrary graphs, right? We can add like another layer here and then like connect this up in some strange way, however we want. But the key thing is that these nodes are basically, can be thought of as sort of the atomic operations, and then the connections are like basically how inputs get fed through an atomic operation to like the next set of inputs, the next sort of set of representations. So basically the sole trick we need to do to turn any sort of arbitrary like computation graph like this into a predictive coding network is we just need to add error neurons to error units, let's say, to every single node on this computation graph. And so basically what this represents is the difference between like the actual value, the value going into the computation, and then the difference between that and basically the predicted value going into the computation. And so the idea is that you can build networks of these things and then run predictive coding as before, and under certain cases, this can actually become exactly the same as backprop. So essentially, the key result is that at the equilibrium, you can show that the backpropagation the errors at equilibrium are approximately the same as the backpropagation gradients from the loss all the way to the actual activity at that layer. And so the way to think about this is basically that the predictive coding will essentially distribute the errors throughout the network to find the place with the smallest error. And then the place with the smallest error under certain conditions is also very similar to the gradient of the error of the loss function at that point, in that if we change the error a bit, then basically that change will propagate through the whole network and cause a change in the loss, and then that is equivalent to the backprop gradient. And so mathematically, you can essentially show that the equilibrium activities have the same recursive structure as backprop. So basically, this is just a bit of algebra here, but this sort of is the key line here, where we show that the errors at one layer are just equal to the errors of the layer above times basically this derivative here. And this is exactly the same as the structure of backprop, where errors are replaced with these deltas, the gradients. And so if the errors of the output layer are therefore the gradients, then recursively, the errors at equilibrium are always the gradients all the way back. So that's sort of that general result. And you can show basically this is actually the case. Convergence is quite easy, although it takes a while of simulation, and that it's basically you can train neural networks with this stuff. And so this is what I was doing in 2020. And so there's also, you can think about various different conditions under which this holds. And so basically the short end, the sum of it is that this holds as long as your gradients, your activities at equilibrium remain close to the activities in the forward pass. And so essentially the way to think about this is that here we can have these terms relating the activities of the forward pass to the errors, to the equilibrium errors, but these are really the activities at equilibrium. And so if the equilibrium diverges quite away from the forward pass, then it won't be the same as backprop, which only uses the forward pass. So the other way to think about it is the predictive coding. The equilibrium of predictive coding is essentially doing backpropagation through the equilibrium and not through the forward pass of the network. And so if the forward pass of the network is close to the equilibrium, then fantastic. We have got original backprop back. But if the forward pass of the network is not close to the equilibrium, if the equilibrium is doing something different, we're actually doing backprop through the equilibrium instead. And so then the question is, like, what does that actually mean? And so this is the very interesting point I'm going to get to next. But like, first, we're just going to quickly have a survey of the literature of how we can actually get it so that the forward pass is basically the same as the equilibrium. And so in the James Whittington paper, what he did is he said the ratio of essentially the top down to the bottom up influence is small. So the bottom up influence is essentially the forward pass going up, and then the top down is the errors coming down. And so if the errors are very small, then they won't influence the equilibrium much, and so it will stay close to its initialization in the forward pass. And so mine is by basically setting the layer-wise gradient close to the free forward pass values, which sort of keeps everything close to the equilibrium. And then similar, Yuhang Song showed in 2020 that if you just directly use the first step of change, not the equilibrium anymore, but just the first update, then this will be as close as possible to the forward pass, and so you will get backprop again. Right, so that's sort of what we've been working on about how predictive coding actually approximates backprop. But essentially the key thing is that we know predictive coding, these conditions are all kind of unsatisfying to me, at least. So this is the motivation behind this work. These conditions are all kind of unsatisfying because if the forward pass is close to the equilibrium, then basically the equilibrium isn't doing anything. And what this means is that the predictive coding network is basically not doing anything different from backprop, and it's kind of forced to do that in a kind of artificial and weird way. And so we really don't want this to happen. We actually want to be able to sort of use the full power and flexibility that predictive coding, this inference equilibrium stuff gives us. And so then the question becomes, if the inference equilibrium is different from the feed-forward pass, then what does backpropping through the inference equilibrium actually mean? So this basically lets you develop a new algorithm, which we call inference learning. And so essentially, the idea is exactly what we said. We first fix the outputs of the network and compute this equilibrium in the middle of all the activities, which we call the inference phase, because in sort of mathematical terms, it corresponds exactly to variational inference. What we're essentially doing is we're inferring the posterior of each layer in the network, given the input and the output layers being clamped to whatever the targets are. Then, given this posterior, you then do learning basically to maximize the sort of log likelihood of this posterior given the weights. And so this does something actually quite different to backprop. And so then the question is, does it do anything better than backprop? Is there any reason to think it's a nicer algorithm? And so the answer to this is obviously yes, right? So if it hadn't been, if it was like a rubbish algorithm, then we wouldn't have any papers written about it. So there's that sort of selection issue. But the key reason that we think IL inference learning is fundamentally better than backprop relates to interference. And so people don't really think about this in backprop much at all. But in backprop, what is assumed is that each of the weight updates you make in backprop are independent of all the other weight updates. So essentially, imagine you have some error at the output, and then you obviously compute two gradients, the gradient of the error with respect to weight 1, gradient of the error with respect to weight 2. Then you basically apply these updates in parallel, and so they're independent of each other. What this means is you can have interference between these weight updates. So like, supposing the error is quite small, or the weight update is big, then basically what you have is two updates which both correct the same error. And so this can lead to like overshooting behavior, where essentially what happens is like you basically go, because you update two weights, they both sort of merge together and strengthen each other, and then you actually end up with an output which is gives an error on the other side, too strong of a change, essentially. So predictive coding inference learning doesn't basically reduces this interference quite a lot. And this is because during the inference phase, essentially the different activities of each layer, they're interacting with each other because of their errors. And so what this means is effectively that the errors in predictive coding are redistributed throughout the network flexibly and sort of dynamically, depending on what the other bits of the network are doing. And so this is a nice visualization from our paper we have on this, which is basically trying to give you a simple example different to the one I gave you about how interference works. So another place you can get interference is if you have two outputs of the network. So the idea here is we have some bear in some like sitting at a stream, and it's sitting at the river and it's expecting to smell some fish which it likes to eat, and it's also expecting to hear the water running down the river. But for whatever reason, like it's I don't know, like it can't hear the water, like its ear is like damaged or something, I don't know. It can't hear the water, and so obviously this produces a prediction error in that it's expecting to hear the water and it can't. And so what this means is if you have this double layer output, so basically the input is like everything it sees here, and then it expects both to see the fish and to hear the river. And then basically if it doesn't hear one of them, then so suppose like this, if it doesn't hear the river, then there's an error here, and then backprop will obviously backpropagate this error all the way backwards through the network, right? And then update all the weights to make it think it's less likely to actually hear the river. And so what this obviously does is it changes the whole network, even though this output was actually correct. It was actually expecting to smell the fish, and it was smelling the fish. But this output, basically, as soon as this network changes, then this output itself will change again. And so basically this, by this prediction error of it failing to hear the river, it will end up actually in the future predicting it's less likely to smell the fish as well, even though that prediction is actually correct. And this is because basically backprop updates all these weights without taking into account essentially what the rest of the network is doing. And so this obviously causes this interference effect. And you can see this would actually be important. Like for these kind of animal examples where you don't want this kind of weird interference between different sensory modalities, say, where like prediction as a one modality affects how you think about other things, other modalities. It's kind of a strange thing to happen. And so predictive coding basically solves this, because during the inference phase, obviously there's an error here, but this error gets distributed back through the network, but it also gets distributed to the correct output. And essentially it's saying like the correct output is given an error because the rest of the network has lots of errors, there's no error here, and so it distributes the error up to here. And then what this means is it updates the weights to this output in a way that takes into account the weight updates being made back here. And so this basically maintains this prediction, even though the rest of the network has changed out from under it, essentially. And so this interference effect actually has quite a large effect on your networks in practice. And so one of the things we've been looking at is, actually, does this make a difference? And the answer is yes, it does. So one thing to think about is, so this happens much greater for deep networks, and it happens much greater for, there's more interference at higher learning rates. And so this kind of explains why backpropagation, you essentially need really low learning rates to do anything in backprop. Essentially because with high learning rates, these interference effects become very large, in that you're basically always overshooting the output, and at high depths, the high learning rates, you're always overshooting the output. And people don't normally do like multiple output neural networks, but this is also something that would happen a lot. So that's one issue with backprop. Another issue with backprop, which inference learning, IL, does better, is that IL actually takes shorter paths through the weight space to reach the correct output than backprop. And so the way you can think about this is backprop makes local updates. So it just takes like a step in the best immediate direction, whereas for all the weights individually. But what predictive coding, IL, does is IL can actually take steps directly towards the correct output. This is because it can sort of accumulate information from the rest of the network during its inference phase. And so one way to think about this is we can actually look at this measure called target alignment, which is basically the angle between the most direct path from input to predicted output to the target, and then the output after you've done some learning. So basically after a weight step. And so this is basically showing the dynamics of backprop versus IL learning some point. The backprop basically, we start out here and we want to go to here. And backprop takes this really long sort of circuitous path through the weight space, whereas IL basically takes a much faster space, much shorter path through the weight space. And this basically will result in faster learning as well. And so we can show basically that for deep networks, there's more interference in target alignment. This measure gets much worse for backprop, but stays the same for prospective configuration. Similarly, prospective configuration can actually, in certain cases, train a lot faster than backprop, because A, it's making these shorter steps, and B, it's got less interference, and so each step kind of counts for more, because it's not having to undo the effect of other weights all the time. So similarly, we find that IL outperforms backprop in various other situations. And so perhaps the most interesting is this small batch online training. So it's well known that basically backprop is really bad at online training. Online training is where you essentially just get one example at a time. So backprop always needs like large batch sizes, and this increases with the size of the network that you have. And basically this is thought to sort of average out various kinds of noise in the data set, but it also helps reduce interference as well by basically averaging out the interference you get from the independence of weights. And so it's kind of crucial that predictive coding IL does much better than backprop on this. It makes sense why, but also this makes perfect sense because the brain can only do online learning. The brain can't like look at a whole randomly selected set mini batch of like 100 visual scenes at a time. It has to only, it's confronted with it has to process what it's confronted with at the moment. And so in these kinds of situations, IL does much better. Similarly, in the small data limit, when there's not a whole lot of data, basically IL does better and learns more from individual data points than backprop. Again, this is something similar to what the brain needs to do, and is what machine learning is currently quite bad at doing because it uses backprop. Similarly, we can also show, interestingly, that IL outperforms backprop on continual learning tasks. So essentially what this is you have basically various distributions of data tasks. You have various tasks you have to do. The distribution changes between tasks. And then, you learn one task, and then you have to learn the next task. And usually what happens if you do this is you have this thing called catastrophic forgetting, where when learning task 2, the network will completely forget how to do task 1 at all. And this is really bad, obviously, and this is probably not something, I mean, it kind of happens in the brain. You obviously do forget stuff, but you don't have this complete catastrophic forgetting that happens with backprop. And so here we show that basically it's not great. So these are different tasks here, and basically performance collapses whenever we switch to a new task, which isn't particularly ideal. But what we show is basically that IL actually does slightly better and recovers a lot faster than backprop whenever there is a switch between tasks. So we know that IL is better than backprop on continual learning. And similarly, we can also show that basically IL performs equivalently to backprop on standard machine learning training paradigms. So like this thing is as good as backprop where backprop does really well, such as large batch sizes with IID data sets, but also does better than backprop, interestingly, in many of the exact situations where we expect the brain to do better. And so this is one of the reasons I think IL is super exciting, and is kind of much more similar to how the brain must work than obviously how backprop works. Because the key thing about IL is that it is a fundamentally parallel and local algorithm. Like you have this inference phase where all the network is converging, and this can be done for every single neuron in the network in parallel and independently of all the other neurons, where the information is exchanged basically all the time about how the local prediction errors change. But like you never get a situation where like neurons have to wait for what other neurons are doing to send them, how to update themselves. This never happens in IL, and this is why I think it's much closer to what the brain is doing, and obviously it built off predictive coding, and the very large amount of evidence that predictive coding or something very similar to that is implemented in the cortex. So IL also has some relatively nice theoretical properties. So like we can actually analyze it in the linear case, and so I have a paper which will be coming out like this week, doing a lot of these kind of theoretical analyses. And another very interesting property is we can show basically that this IL algorithm essentially interpolates between what backpropagation does and what target propagation does. And where target propagation is obviously computing these local targets, what we can think about the IL algorithm as these sort of the errors at equilibrium, the activities at equilibrium are effectively kind of like local targets in that they're how the network should update itself, should evolve over time in order to better match the data. And you can kind of think of this itself as the process of Bayesian inference, where essentially what we have is we have a prior, which is where we start in the forward pass, and then we have some data given to us, which is like the correct input target association, and then we want to compute the posterior of that activity given the likelihood, obviously, and which is the data, and the prior, which is the feed-forward pass configuration. And then this actually obviously corresponds to the posterior for the layer, which is exactly what the equilibrium activities of the network actually represent. So another way we can think about this in the same sort of setting is that IL basically computes these local targets, but with priors to make them stay close to the feed-forward pass initialization, which is obviously helpful basically so you don't completely overfit your network to every single data point that you get. You want to kind of stay relatively close to what you're already thinking is good, but then obviously also gain some advantage from using this local target update rule. So other things that we can show is that basically we know that IL can actually converge to a minimum of the loss function. So this algorithm is actually a reasonable one. It actually will converge about as well as backprop, and it has very similar convergence properties to backprop. And essentially the idea is we can think about IL as basically from this variational EM algorithm, which is also, we can think about this as being related to target prop again, in that we can think about minimizing the free energy as basically minimizing a constrained version of the loss function minimized by backprop, where the loss function is where the sort of additional constraints are basically to stay close to your feed-forward pass priors. And so essentially we know that IL will converge to backprop. We have lots of experimental evidence for this. And so what this kind of means is that this IL algorithm is really nice. It is completely parallel, it's completely local, and it's basically predictive coding, which is an algorithm we know has a fair bit of evidence for being implemented in the cortex, or at least it's like a very promising contender. We know that this algorithm does at least as well as backprop on like many tasks. We know it can converge to minimum for loss functions. It can be applied to arbitrary machine learning architectures. And we also know that it does better than backprop in various situations which are actually relevant for the brain, such as the continual learning and the small data, the online learning, all these kinds of things, which is basically where backprop doesn't do well, but IL does do well. And so furthermore, it has very nice theoretical properties, like it reduces these weight interference effects. One thing I want to test out is whether it actually helps deep networks be trained effectively. So like in classic machine learning, you can have very deep networks, but like typically you need to use residual networks, ResNets, because essentially the issue is signal propagating through the networks is really bad. And so IL might be able to help solve some of these vanishing gradient issues you can get with backprop. And finally, IL is also much more flexible with test time behavior. So basically, I've not really talked about this at all, but IL, instead of clamping the input and the output of the network, you can basically take posteriors over arbitrary subsets of the network. So you can say like, I want to clamp some, layer 3 of my network to something, and then tell me what the layers like, layer 4 does, but also tell me what layer 2 does. And this kind of clamping is unique to IL. It can't really be done with backprop trained networks in a very easy way. And so this could also be a way for like the brain, basically different regions of the brain to interact with each other. They can interact by essentially clamping or conditioning, sending basically data to the inside of the network, not just to the input-output interfaces, but to anywhere in the network, and then they can sort of read out different queries you can make to the network. So I mean, I think personally this is a very nice algorithm, and so we've got several papers written on this at the moment, and I think it's quite a nice thing in that we can actually go beyond the sort of standard backprop and like, hey, can the brain approximate backprop? Instead, we can say like, no, there are actually better algorithms the brain can use, which not only are easier for the brain to implement, more natural for it to implement, have nicer parallelism properties, locality properties than backprop, but also do as well as backprop or better. And I think that's quite a big statement to make, actually. So that's been really nice, sort of figuring all of this out. And so obviously we have a lot of future work planned. Like the main thing is we want to scale up IL inference learning to these extremely large scale models to verify that it can still do as well as backprop in these situations. We similarly have ideas about, improving the way inference is performed, because at the moment we're just doing this gradient descent on the free energy, but in practice, this is really just a case of arbitrary, like standard posterior inference. And so we can use like message passing algorithms to figure this out. We can also look at like where the causal inference works in these models, and understanding better the conditions when IL does better than backprop, essentially. And finally, we should look at this sort of probabilistic interpretation of this network, whether it leads to better robustness and calibration, because artificial neural networks are often really bad at estimating their own uncertainty. But because we have this full probabilistic characterization of the network, maybe we can do better at estimating the uncertainty than standard backprop NNs, which aren't trained to do that at all. So thank you very much. And that's my presentation. So I'm just asking